The topic of today's discussion is about the hybridization. Now, this lecture is going to be made super duper easy via this example, this definition. If we understand this definition, then this entire lecture will become easy for us. So now let's start the discussion from this particular definition. Definition is atomic orbitals of same or nearly same energy. When they intermix, they give us same energy orbitals. This mechanism is known as hybridization. Definition is a little bit difficult for you guys now. Well, as I go on explaining the definition to you guys, the topic will become and the definition will become very easy for you guys. Yes, I guarantee this is going to become easy for you guys. Well, first of all, let us crack the definition. Let us understand the definition first of all. Atomic orbitals. First of all, the very first thing that we don't know, most of our students don't know, is orbitals. What is orbitals? The very first point that we must understand. What is actually orbital? We know about the atom, an atom like carbon. Now, what is orbital of the carbon? What is mean by the atomic orbitals? Means orbitals of the atom. So atom is carbon for us. What is actually the orbital? The question is, what is the orbital of an atom? Simple answer is that we have a carbon here, and now if you go in the depth of the carbon, you will get what? Nucleus. Nucleus is surrounded by a shell, and that shell contains subshells. In those subshells, there are certain chambers, portions, where there are electrons available. This is called nucleus, this is called shell, and this is called subshell. These chambers are called what? Orbital. Very simple. What orbitals are actually? The portions or the chambers where electrons are available or where electrons are actually found. I hope you got the definition or the concept of the orbitals. Simple. Nucleus surrounded by the shell. Shell contains subshells. In the subshells there are certain portions, certain chambers known as orbitals. In the orbitals there are electrons. Got? Very simple. Remember, each and every orbital contains 2 electrons. And the rest of the definition regarding orbitals, we have explained this also in a little bit explained manner in our other videos. You can search that complete video for orbitals. So for now, in order to make you guys understand about this hybridization, I just gave a review of the orbital here. We have explained this also. Okay, you can watch another video for regarding the orbitals. Coming to the point back here, atomic orbitals. So we got the definition or the concept of the orbitals. Orbitals are the chambers in which electrons are available, and the orbitals are present in the subshells. Subshells are present in the shells, and shells are responsible to surround the nucleus. Next point is that atomic orbitals of same or nearly same energy. Now question is, what is same or nearly same energy? What are the orbitals of same energy and nearly same energy? The question is this. Now let's know the answer of this question. Very simple. We have the same carbon hereby, and we know that atomic number of carbon is 6. What is going to happen? Nucleus is here surrounded by the shell. Number 1 known as K shell. Then we have another shell that is called L shell. In the K shell we have a subshell known as S subshell. In that there is one orbital. Remember guys, we have explained orbitals in our other video. So here is just a kind of chart for you guys from that video to make you people understand about the hybridization hereby. Okay, well, K shell we have one subshell, and that one subshell is having one orbital, and one orbital is actually having 2 electrons. Okay. Now here comes the next one, that is the L subshell. I have told you guys in the beginning, if it is the first shell, there will be one subshell. If it is the second shell, that shell will be containing 2 subshells. And if it is the third shell, then that must be having 3 subshells. So subshells are actually directly proportional. When the number of shells are increasing, the same likewise the number of subshells will be increasing. So we are talking about the second shell. So second shell is the L shell. The number of the shell is 2, so the number of subshells must be 2. That is S and P. The second subshell will be P. So here we got 2 subshells, and regarding these subshells we have got a discussion hereby that in the first subshell we will be having 1 orbital, in the second subshell we will be having 3 orbitals. So total becomes how many? 4. So 4 orbitals are actually in the L subshell for now. So what will happen now? 4 orbitals. 3 orbitals, in each orbital we have 2 electrons. So 4 multiplied 2 equals 8. So 8 electrons can reside in the L subshell. So now in the case of the carbon, how many electrons are supposed to be available in the L subshell? Very simple. Atomic number of carbon is 6. So what will happen? First shell, that is K shell, and then we have S subshell. There will be 2 electrons available. Why? Because S, there is one orbital, and in one orbital there can reside only 2 electrons. Then we have the L subshell. In the L subshell we have 2 subshells, S and P subshell. We got the concept that in the S subshell we have one orbital and there can only come 2 electrons. Now remaining of 6 is 2. So P is a second subshell of the L shell, which can reside how many electrons? 6 electrons can reside in the P subshells. Why? Because P subshell contains 3 orbitals. In each orbital there are 2 electrons, so 3 multiplied 2 is equal to 6. So we will get how many electrons in the P subshells? 6 electrons. So now here, if I write 6 here, by then the total number will become 10. But in case of carbon, we have only 6 electrons in the entire shells, K and L. So what we are supposed to write here is just 2. 2 plus 2 plus 2 equals 4. So 6. So here we got our atomic number being complete. So what we got now here, the configuration, that is actually writing the number of electrons in the subshells. Now the question is actually orbitals of same and nearly same. What is actually the main concept of behind these 2 points? What is actually the orbitals of same energy and nearly same energy? So in case of carbon, if this carbon is supposed to interact with another atom like hydrogen, so what it's supposed to do is it is actually supposed to change its configuration. It is supposed to change its conformation. You can say it is supposed to change its structure. It is supposed to change its orbitals. How? Like there should be a kind of hybridization or a kind of mix-up being observed. Very simple. Just concentrate. What will happen? Actually, the L shell is responsible to interact with other atoms. Suppose if we are going to form CH4, so what will happen? In this case, carbon will interact with the hydrogen, 4 hydrogens. So how this carbon is going to interact with the 4 hydrogens is very simple. Now you just concentrate, you will get the entire discussion. What I mean hereby to make you people understand is actually concentrate on the L shell. The L shell is responsible to interact with the 4 hydrogens. How? Very simple. So here we get our L shell, and that we have subshells S and P. So in the S we got 2 electrons, and in the P we know about this point very well, that P is actually having 3 orbitals. In the first orbital, second and third orbital, there are actually electrons supposed to be available. So I told you in one orbital there should be 2 electrons, but now in this case we are actually moving towards the formation. For now, just consider in one there can be 2 electrons. Okay, so what we got here now, in case of carbon, our 1s is there, px is there, py is there, pz is there. In the s we have 1 orbital, in the p we have 3 orbitals, and in each we got this point. In each orbital there is a place for 2 electrons. So in case of carbon we just have 6 electrons, so 2 of the electrons are in the K subshell, orbitals of the K subshell, and remaining 4 electrons can be placed in the orbitals of S and P subshells of the L shell. So now what happened? S got 2 electrons, P got px, py, pz. In the px we can place 2, but according to Hund's rule, what will we do? We will just first of all fill the remaining energy orbitals like this. So we are supposed to move this electron from px to py. So what will happen now? Pz will be actually a kind empty for the electrons. Now this carbon is actually in the ground state. What happens now? This carbon says I want to interact with hydrogen and I want to form methane. So how will this interact? There is only one possibility with this carbon, that is, it must shift the electrons from the s orbital to the pz orbital of the p subshell. S subshell contains one orbital in which there are two electrons available, and P subshell contains three orbitals, but two of the orbitals are actually half filled, and the third one is not having any electron when it is in the excited state. What will happen? This will do the transfer here. This transfer will take place from the S orbital. That is, one of the electrons will move towards the P. Like this, what will happen? This S will interact with the P orbital. So what happened now hereby? 1, 2, 3, 4. These four, 1s and 3p, will interact. They will intermix. They will do intermixing, and they will form orbitals of same energy. Now here, the energy of s orbital is different from the orbitals px, py, pz of the p subshell. So now the orbitals of the s subshells are different from the orbitals of the p subshell. What happens when there is a transfer observed from the s subshell to the p orbitals? So what will happen then? Then mix-up will take place, and all these s, p, 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 they will mix, and they will actually give us four orbitals of same energy, and they will be given the name is sp3 orbitals. sp3, sp3, sp3. Now what is happening here? By atomic orbitals of same energy. Now these orbitals px, py, pz, they are actually of same energy. They are of same energy or nearly same energy. Now the orbitals of the p subshells are having actually same energy. When we talk about the px, py, pz, py, px, py, pz are actually having same kind of energy. But when we compare these orbitals with the orbital of the s subshell, then what will happen? There will be a slight change available, or slight change will be seen. Why? Because this is another orbital. This is not the orbital of the p. So like this, these orbitals, the three orbitals of the p subshells are same for each other, but the orbital, that is the s, this is different for these orbitals. But now, due to a common shell, that is the L shell, these both orbitals will be having same energy, nearly same energy. So s orbital is having nearly same energy with the px, py, pz orbitals. When we compare all these, s is having a kind of similarity, this is nearly similar, a kind nearly same with the x, y, z of the p subshell. So what I'm telling you guys, what I'm just trying to make you people understand about the point is that is very simple, that this is actually a little bit different in case of energy when we compare with the remaining orbitals px, py, pz. Now px, py, pz, they all are actually same. So what the definition is talking about is atomic orbitals of same energy. Atomic orbitals of same energy. So these are the atomic orbitals. Carbon is having orbitals, okay, number of orbitals. Here you're talking about the L shell. In the S shell we have S and P subshells. In the S subshell we have S orbital, one orbital. In the P we have three orbitals. Now all these three orbitals are actually same, having same energy. But when this is compared with these two, then there is a little bit difference being seen. So these same energy orbitals, when they mix with slightly different, nearly same energy, nearly same, these are actually having energy nearly same to this orbital. So all these orbitals, same energy orbitals and nearly same energy orbital, when they mix together, they will give us orbitals having same energy. So now here, after when they mix up, then the product which is formed of the orbitals, those orbitals will be of same type. They will behave in a same manner. Means all are actually now equal in case of energy. So this phenomena in which same energy orbitals intermix with nearly same energy orbital to form the orbitals of same energy, this phenomena is known as hybridization. This process is known as hybridization. Hybridization is actually the mix-up. So here what is happening? The hybrid is actually formed. Hybridization, the mix-up is actually formed, and that mix-up is actually providing us equality in sense of orbitals. So that's why they are then named as sp3, sp3, sp3. So we generally study hybridization of three types: sp, sp2, sp3. If one S, one P join together, this is called as sp hybridization. When two P and one S hybridize, they will form sp2. When three P, in case of this carbon that is supposed to be of methane, sorry, so they will actually form sp3 hybrid orbitals. So this is the methodology of the hybridization or hybrid formation, or the hybridization process, and the definition. I hope you got the understanding. And for further information, please do visit our lectures on SP, SP2, SP3. Until now, this is all about the hybridization. I hope you got the definition and understanding. If still you have confusion anywhere, feel free to ask us in the comment box. And thank you for watching.